Hi everybody. Today I thought we'd have a go at designing and building a pulse generator that is capable of giving us a square wave output from just a few hertz all the way through to 1 megahertz, and at the same time giving us the ability to alter the pulse width by adjusting the duty cycle of that square wave. Now, in order to do this, I'm going to use a small IC from Linear Technology, which just happens to have built into it a lot of the features that we require today, and these include things like the voltage control oscillator and a pulse width modulator circuit, plus one or two other additional items as well. So I think the first thing we'll do is let's have a look at the IC that will form the heart of our project today. I'll just talk you through that, and then we'll have a look at how we apply that to our particular project. Right, well, here you see the IC which will form the heart of our project today. It's the LTC6992 from Linear Technology, and this particular IC does actually come in 4 variants, and the only difference between the variants is the range of the pulse width modulated output, i.e. the duty cycle variance of the square wave coming out, but I'll cover that a little bit later. So let's just have a quick look at the overview of this. The heart of it is a master oscillator, and the frequency of that master oscillator is set by the resistor on pin 3 of the IC. And what's happening here is that the oscillator itself, the frequency is a function of the reference voltage on pin 3 and the current flowing through the set resistor. Now, as you can see here, we have a voltage reference source in the IC. This is a plus 1 volt reference source which is fed to the non-inverting input of the op amp there, and this arrangement with the MOSFET we have there is keeping the voltage there on the source of the MOSFET on pin 3 fixed at the reference voltage. So in other words, the reference voltage inside the IC at plus 1 volt is what's maintained on pin 3, and that's what's fed to the master oscillator in the IC. And simply by adjusting the value of the resistance of the set resistor there from pin 3 to ground, we can alter the current flow to the master oscillator circuit, and that alters the frequency. Now, the range of this frequency, or the range I should say of the RSET resistor there, is capable of changing the current from something in the order of 1.25 microamps all the way through to 20 microamps, and that would mean that the typical range of resistor value there can range from 50k at its lowest all the way through to 800k at its highest. So that resistor, or the value of that resistor, sets the frequency of the master oscillator in this IC. Now, the output of that oscillator is then fed into a programmable divider circuit, and that itself is controlled by a voltage that is going in on pin 4 of the IC, labelled div, and that voltage going on pin 4 controls the output of a 4-bit analog to digital converter, and the first 3 bits of that ADC control the programmable divider, and that gives us from 0 to 15, so 16 possible combinations that the programmable divider can achieve in terms of dividing the frequency output. The most significant bit from the ADC there is fed to a circuit called the output polaritor, and that actually determines whether the pulse coming out on pin 6 of this IC is either positive going or negative going. So simply altering the most significant bit of the ADC, we can control the output of the oscillator there on pin 6 and determine whether the pulse is positive or negative going. So this gives us a very simple way of selecting a range within the frequency of the master oscillator, which is then fed to our output. Now, on the way to the output, the next stage it goes through is a pulse width modulator, and that gives us the ability to then alter the duty cycle or the pulse width of that square wave at the output pin, pin 6. And to alter that duty cycle, we feed a voltage into pin 1 of the IC. That modulates the frequency and alters the mark space ratio. And that first of all goes through a voltage limiter, because the range at which we can alter the mark space ratio depends on the version of the IC itself. And I said earlier on that this particular IC comes in 4 versions, and each version has got a digit at the end, so it'll be a -1, -2, 3 or 4, and that determines the range of the swing for the duty cycle. So version 1 of this IC allows us to go from 0% to 100%, altering the duty cycle. Version 2, which is the one that we're going to use today, allows us to go from 5% to 95%. And then we have version 3, which allows us to go from 0% to 95%. And finally, version 4 allows us to go from 5% to 100%. So the only difference between the 4 versions is the limits to which the pulse width modulator can alter the duty cycle on the output. So as I say, the version that we're going to use today is going to be the LTC 6992-2. Now this IC can operate from a supply voltage of anything from 2.25 volts all the way through to 5.5 volts, and we're going to feed it with a 5 volt supply in our project today. Right, here we have the block diagram of the project today. There is the heart of our project. That's the little IC that's got the oscillator and the pulse width modulator circuit in. That's the LTC 6992-2 in our case today. And as I explained, the 3 control pins there, pins 1, 3 and 4, pin 3 sets the frequency by simply having a fixed resistor, or in our case we have a variable resistor going from pin 3 to ground, and that will alter the frequency of the oscillator. And that's simply done by adjusting the resistance value there. According to the datasheet, we need to vary it from around 50k minimum through to 800k maximum, and that will then work within the range of the IC, which is around just over 3 Hertz all the way through to 1 megahertz. I'll be using a 1 megohm linear pot there to do that job, but I'll be adding a few resistors on that to limit its range. So I'll have a series resistor that will limit the bottom range by 50k, so I'll probably put a 51k resistor in series with that, and then to restrict the maximum resistance value to around 800k, I'll put a 3.9 megohm resistor across the potentiometer, and we'll see how that functions. So the variable pot there sets the frequency of the oscillator by controlling the current for the master oscillator. The programmable divider inside that IC is determined by the voltage we feed on pin 4. Now, when we have a little look at the data sheet, they do give you a table which shows you the voltage ranges that you need to use for all the ranges for the programmable divider, and we'll come back and have a look at that. But suffice to say, for the moment, adjusting the voltage on pin 4 simply programs the divider in the chip. And to do that, what I'm going to use is a 12-bit DAC, a digital analog converter IC. I'll be using a little MCP 4725 IC. These are little tiny chips. Again, it's a TSOC23 6-pin package, and it operates on the I2C bus, which means that we can program it by just 2 wires from the Arduino Nano. Now, the Arduino Nano, to use the I2C bus, we utilize pins, analog pin 4, A4 and A5. A4 is the data pin and A5 is the clock pin, and it's those 2 pins there that feeds pins 4 and 5 on the DAC that controls the output voltage that eventually comes out on pin 1 and drives pin 4 of the oscillator IC. Now, with all I2C bus ICs, you need to have an address. You need to obviously address that particular chip as opposed to any other chip on the I2C lines. And the address of that IC is determined by the logic level on pin 6 of the IC. It's labelled A0. And whether we take it high or low determines what the address will be. In this case, we've taken it high, and that selects the address for that particular 12-bit DAC. Now, the signal that drives that DAC is determined, the digital signal is determined by a rotary switch here. I'm using a 12-way rotary switch, which I'll limit to 8 positions, and we'll have 8 possible ranges on our project today. And all I'm doing here quite simply is using a potential divider between ground and plus 5 volts, and as I flick that selector switch up through that divider, we'll get a different voltage onto the centre of that selector switch, and I'm feeding that voltage onto analog pin A0 of the Arduino Nano, and then we'll use software within the Nano to determine that voltage, and that will determine which position I'm in, and we'll use that information to then program the DAC with the required voltage settings for the divider in the oscillator chip. So we'll have 8 ranges there that will determine the voltage coming out of the DAC. Now, the other pin on the oscillator IC here is the mod pin, pin 1, and that will set the duty cycle or the pulse width. And the crucial thing here is that that requires a voltage range from 0 to around 1 volt, which needs to be quite stable. So what I've decided to do here is use a voltage reference source. I'm using a 1.024 volt voltage reference source, and the IC I'm using there is a Texas Instrument IC, the LM4140, to give us that voltage. And then I'm using a 100k pot to tap it off to pin 1 of the oscillator IC, and that will then give us a voltage range from 0 to 1 volt, and that will control the pulse width of the output signal there. Now, in order to get that information on our display for this project, I'm also tapping off that voltage on pin 1 and feeding it back to the Arduino Nano on analog pin A1, and then we'll measure that voltage reading and feed the resulting information out to the liquid crystal display. So on the display, the idea is that I not only want to have an indication of what frequency range I've selected here, but I also want to have an indication of to what the duty cycle is, or the pulse width is, on the display as well. Now, the display in question I'm going to use today, I'm going to use a 20 column by 4 line display, and the main reason for that is that I wanted to have the ability to add other features later. So I'm using a slightly larger display than we've used on earlier projects, but this time I've decided that rather than drive it the way I've done previously, using all the digital pins on the display, I'm going to drive it from the I2C bus to reduce the number of pins we use on the Arduino Nano. And in order to do that, we need to use a little I2C bus adapter module, and again, you can purchase these quite cheaply on eBay these days, little tiny module that solders onto the display and then gives you 4 wires coming out, a plus 5 volts, a ground, and then you've got the 2 signal wires for data and for clock. So we can now feed the I2C bus to that little adapter that drives the display, and again you can see now that we're using the same 2 lines that we use to drive our 12-bit DAC, but what we'll do is ensure that the LCD display, the address for that display, will be different than the address we have for the DAC, so we can distinguish between the 2 when we're sending the information out from the Arduino Nano. Now, in order for the I2C bus to function correctly on the data and the clock lines here, we need to have a couple of pull-up resistors. I've not shown them here, but from A4 and A5 I'm going to use 10k resistors going from those pins to +5 volts, and that just pulls up those pins high on the I2C bus. Now, in addition to those controls we have for the oscillator, remember we can also alter the polarity of the pulse coming out. We can either have it going positive or negative, and that's done by altering the most significant bit, remember, of the information that is used for the programmable divider inside the IC. And what I'm going to do today is use another one of the analog pins on the Nano as a simple switch option there that can either be high or low. What we'll do is in software we'll set A2 to use its internal pull-up resistance. It's normally high, but we can then take it low to ground through a straightforward switch. And depending on the position of that switch, we'll send a signal out to the 12-bit DAC, which alters the most significant bit of the data in the divider, programmable divider in the IC, in such a way that we alter the polarity of the output signal going out. And we'll show you a little bit later just how we achieve that. So there we have the block diagram I've put today. And I think the next thing we'll do is we'll just have a look at a little bit more detail of the circuitry around this area here, and also how we select the voltages for the 12-bit DAC. On page 15 of the datasheet for the LTC 6992 you'll find this information, this table, and this shows you the frequency ranges. You'll see here that the frequency ranges go there from 62.5 kilohertz to 1 meg, that's one range, and then the range below that is 15.63 kilohertz to 250 kilohertz. So you'll see that we've got different stepped ranges there and overlapping as well, and there's 8 possible options, and that's the reason I've got 8 options on our project today on the selector switch. The first 8 options there are with the polarity of the output square wave in one direction, so you can see the polarity there is all set at 0, and the next 8 options, which are the same frequency ranges, the polarity you see there is set to 1, so it's for the other polarity. So if you want to switch between a positive or negative polarity of the output signal, you simply need to choose 1/2 of this table to select your frequency range. Now you'll see here that the divider inside the IC, when we program it, these are the options that we have. We have divide by 1, so that stays the same. Then we have divide by 4, divide by 16, divide by 64, divide 256, 1024, 4096 and 16,384. So they're the divider options that we have, and they're determined by the voltage that we set on pin 4 of the oscillator IC. And what they indicate here is that they've got resistors here, R1, R2, which provide a potential divider across the +5 volt supply in our case, and that will provide you with the required voltage for these ranges. But we're not going to use a straightforward resistor divider as they're showing here. We're simply going to generate that voltage using the digital to analog converter IC I showed you in the block diagram. So the important thing we need to look at is the end of the table here, and this information gives us the voltage factor that we need to use to drive pin 4 of the IC to get the selected range. So you'll see here, if we take, say, the second one down, you've got a factor there which is 0.09375, and simply you multiply that factor by your supply voltage. In our case it's 5 volts. So multiplying that by the +5 volt supply will give you the voltage you require to select that particular range of frequencies. And we'll do exactly the same for all the other frequency ranges. Now in the other half of the table here, where we've got the polarity of the output square wave changed, so we've gone from positive to a negative signal coming out in terms of pulse, we simply need to use those factors again, multiplied it by the plus 5 volt supply to give us those voltage requirements as well. So once we've calculated all those voltages, we then need to program the 12-bit DAC with the digital information to give us those voltage outputs that we've calculated to drive the oscillator IC. Right, here we see a little bit more detail of the wiring for the three ICs for this project. There's the voltage reference IC, so I'm showing here the wiring connections for that. The pins 1, 4, 7 and 8 all go to ground. The V-in, voltage in for that IC, is on pin 2, and you'll see here that the enable pin we've strapped to the input V-in pin, and that ensures that the output is constantly on. So we get a constant output coming from pin 6, giving us our reference voltage there of 1.024 of a volt. Now the output there is decoupled by a 1 microfarad tantalum capacitor, and then we're feeding that across a 100k potentiometer, and it's that potentiometer that controls the duty cycle by simply tapping off a voltage and feeding it to pin 1 of the oscillator IC. Now we also take that same voltage to the analog pin A1 of the Arduino Nano, and that's what we use to read that voltage and then finally show it as a duty cycle reading on the LCD display. The oscillator IC itself, you've got the ground pin is pin 2, the set pin, pin 3, is what we control the frequency on, and that's done by that resistor network there going to ground. Remember, we had a 1 megaohm potentiometer setting the frequency of this oscillator, but you'll also recall that when I explained a little bit about the IC, we may need to limit the upper and the higher limit of that range, and hence the reason why I put there a 51k in series with the potentiometer to limit the minimum resistance to around 50k, and I've put a 3.9 mega across it to try and limit the maximum resistance to around 800k. But we'll play around with that in a more practical sense when we get down to building the project. So we may change that later. The output from the oscillator IC is coming off pin 6. The pin 5 is simply the supply voltage of the IC going to the 5 volt supply and then decoupled with a 0.1 capacitor. And pin 4 is the diff pin, and that's the voltage input there determines the selection of the frequency range in the programmable divider inside the oscillator IC. And rather than just have some resistor divider networks there, we're using this DAC MCP4725, and that's going to supply the required voltage to pin 4 to select the range. Now the supply to the DAC is coming from the 5 volt supply to pin 3, and that's decoupled again with a 0.1 microfarad capacitor, and pin 2 is the ground pin of the IC. Pin 6 selects the address for that particular DAC because we're going to program it using the I2C bus, and we have one of two options. Pin 6 is labelled A0. The IC has got A0, A1 and A2, but A1 and A2 are internally programmed at manufacture in the chip, so we've got no access to that. So we can only control the last bit of that address, and we can take it high or low, and in this case I've taken it high through a 10k. Now the output, or should I say the input driving the DAC, which is the data and the clock signals on the I2C bus, they're going to the Arduino Nano A5 and A4, and we've also taken those high through 10k resistors to the plus 5 volt supply, which is a requirement for the I2C bus. So that's the reason for those two resistors there. So that's the little bit more detail of the wiring arrangements for those three ICs. Here we have the display module that I'm using on the project. This is the 20x4 display, and then just below it there you'll see we've got the little adapter module, the I2C bus adapter module, and that's using the PCF 8574 input-output expander IC there, you see, which is a Philips IC. And you've also got a little trim pot there, which we can alter the display brightness as well. So the idea is that if you purchase one of these little adapters, quite cheap really, it comes with all the pins soldered, and you simply feed that through to the pin connections on the liquid crystal display, and then just solder that on. There you are. I've got the that little board now soldered onto the display and ready to go. Here we see the small printed circuit board that I've made for today's project. I've decided on this occasion to use a larger number of surface mount components to try and keep things tidy and as neat as possible, and also reduce the length of connections between the ICs and the components. The two small ICs we're using are TSOP 23 6-pin packages, very small, and they're in this location of the board, and I've indicated on the board pin 1 of those ICs with a small dot, as you can see there and there. The other surface mount IC we're using is a slightly larger surface mount component, and that's mounted here on the board. Again, I've indicated pin 1 with a small dot there, and this area here is the surface mount IC for the 5-volt regulator that we're using on today's project. All the other components on the board are mainly going to be surface mount resistors and capacitors, and I'll show you as I go along with that. The rotary switch is located in this area here, mounted through from the other side, and the Arduino Nano I'll be positioning it on the print side of the board. So I'll mount it here with the pins going through, which will allow us to have some extensions and updates to the project later. The other thing I decided to do is put some pin connections on for the switch and for the potentiometers used on this project, and I'll show you those as I go along. Well, I think the first thing we'll do, we'll mount the components associated with the power supply arrangement for this board. So this area here, so I'll mount the 5-volt regulator IC and its associated capacitors, and then we'll come back and test that before we mount the other surface mount components on the board. Here we see now I've mounted the components for the power supply area of the board, and I've just quickly tested that, and we've got 5 volts coming out, so that's working fine. I'll just point out a couple of things here. Mounting the surface mount capacitors there, no issue with the 100 nanofarad capacitors because there's no polarity on those, but on the electrolytic there, the dark band there, the black band on that side is the negative side of the electrolytic, and on the tantalum capacitor there, the 10 microfarad, you'll see that there's a stripe which indicates the positive side of the tantalum capacitor. So I think the next thing we'll do now is, having satisfied ourselves that the 5 volts is okay, I'll mount the other surface mount components on the board, including the ICs. Right, we'll now have all the other surface mount components mounted. There's the 10k resistors which relate to the selector switch. There's the voltage reference IC, there's a 1 microfarad tantalum there, and the other components are around those two ICs there. I'll just zoom into that so you can see the layout of that. Right, well, the next thing I'll do, I'll just put the pins in which connect to the potentiometers and the switches, and we'll come back and have a look. Here we now see I've mounted the pins on the other side of the board. These two groups of 3 here feed the 2 potentiometers, one for the frequency, one for the duty cycle, and this 4-pin connector there, that's going to the display module, that's the I2C bus. And also you'll notice I've put 2 shorting links here, jumper links, there and there. One is ground and one is plus 5 volts, so you can use them as test points for the power rails. What we're going to do next is I'm going to mount the pins. These pin connections come with the Arduino Nano, and the longest side of the pins I'm going to push through the slots on the PCB there, and just push it through until you can feel the pins there coming through on the other side, and that then gives you sufficient space to then solder the pins here on the print side of the board. So let me solder this one in here. I'll come back and show you that. Here you see now the pins all soldered in place with the plastic spacer now removed. It's a little bit difficult to remove, I found, so I ended up snipping every couple of pins, and then it pulled off quite easily. So I'm going to do the same for the other side, and those are the pins that we're going to use to mount the Arduino Nano on. There we have all the pins mounted and soldered on the PCB, and the idea then is that the Arduino Nano will then slot on top of that and we can solder that onto there. Or alternatively, if you didn't want to solder it, you could get some connectors, these type of connectors, and simply you fix that onto the Arduino Nano, solder that on, and then it would then just plug onto the board. So if you wanted, you could use two of those connectors. We now have the Arduino Nano mounted onto the print side of the PCB. I did decide to solder some inline connectors onto the Arduino so it plugs into those pins that we previously soldered onto the PCB. So I think the next thing we'll do now is we'll solder the rotary switch onto the board. This mounts from the other side of the board and then solders on here. Right, here we have the completed printed circuit board with all the components mounted. You'll see here I've got two pins there which are going to go to the switch. Here we have the module now all wired up to the display with the 4-wire cable there. The frequency control I've mounted on the board as close as possible. Frequency range switch. This little socket here is going, flying leads are going out to the polarity switch to flick the negative or positive pulse output, and I've got another flying lead cable there going to the duty cycle control. So there we are, that's it wired up. So I think the next thing we'll do now is we'll connect it up and have a look at the output on the oscilloscope. Right, well, I have the unit all wired up here. The software is installed on the Arduino Nano, and just to make it easier to view the display, I've just mounted it on this little frame adjusting mount here. I've got the output from the module connected to the oscilloscope and also to the frequency counter, so we can check the shape of the square wave and the mark space ratio, or the duty cycle, and also have a look at the frequency. And there's the duty cycle pot, and as I say, the frequency one is on the board, as is the frequency range selector switch, and the little single pole switch here is where we can change the polarity of the output signal, either positive or negative. So I think the next thing we'll do, we'll power up and have a look at the startup display and then just check it on a frequency. So I'll just connect the 9-volt power pack, and you see on the display there we've got the startup screen. After a few seconds it'll then revert to its normal operating mode, and you see we've got frequency range on the top, and below that you've got the frequency range we've selected by the rotary switch. In this instance I'm at the bottom end, so I'm 3.815 Hertz to 61 Hertz, and you'll see here the duty cycle at the moment showing 47.92%. If you look on the frequency count, it's actually showing as a frequency of 5 Hertz, so we may have to trim that, so it's unless I've got the pot here, it's not quite at the end. So let me just turn it to the end. That's right. So I've got the control turned to minimum, and we're reading a frequency there of 3.4 or 3.39 Hertz. According to the datasheet, we should be getting around 3.81 Hertz at that bottom end, but we can probably trim that with the resistors on the padding resistors on the frequency control. There's the clean square wave you'll see there, and if I alter the mark space ratio, the duty cycle control there, you can see we can change the duty cycle of that square wave from 5% to 95%. I'll just leave it there for the moment. Let me just switch up a range to a slightly higher frequency. So that's the next range up. So we're now at a range which is around 15 Hertz to 240 Hertz. Again, we can alter the frequency control and adjust that frequency, and you can see the frequency output there showing on the frequency count. Again, that's showing slightly lower than what the range setting is. Again, it's probably just the padding resistors on the 1 mega ohm pot. Let's just go up another range. So we're now at 61 Hertz to 976 Hertz. And there's the waveform again, and it's showing 54. Let me go to one end, the maximum end, and that says 957. According to the range, it should be 976. So our range is slightly out with respect to what we're seeing there on the frequency counter, but it's really just due to the resistor arrangements we have on the frequency control. So if we just have a look at the altering the Mach space ratio now, you can see there we've got a nice clean movement from, you'll see on the display there, it gives you the percentage of the duty cycle. As I alter that, you can see that percentage change. So at that end we've got 5%, and at the other end we should have 95%. Now what we'll do is, if I flick the switch here and see if we can invert that pulse on the output. There you go. So just flicking that switch, we are switching the output pulse either one way or the other. So let me just go back to around 50% duty cycle or thereabouts. So we're showing 49.7, well, it's around about 50% anyway. Let me just go up another frequency range. I've now got the frequency selector switch for the range 15.63 kilohertz to 250 kilohertz, and we're towards the top end of that at the moment, so we're showing 245. Again, I can alter the frequency control again here, and this time we get a lot of noise as we adjust that frequency. And it takes a while, I think, to settle, so we need to have a look at that. Again, we can alter the Mach space ratio. If I go up again in frequency, and this is where it becomes a little bit unstable actually. What I'm noticing is on the higher frequency ranges we do get a bit of noise and instability as I'm altering the control there. I take my fingers away and it settles down again, so it doesn't like the pickup the capacitance from your finger anywhere near that control, so we may have to have a look at that. We don't get that problem at the lower frequencies, but we do get it at the higher frequencies. Again, we can still change the Mach space ratio. So let me just go back down again to the lower frequencies, and on the lower frequencies it's much more stable, and again altering the Mach space ratio. What I've found now is that if I earth the casing of the frequency potentiometers, I've just clipped a little crocodile clip on there and then taken that flying lead down to ground, and I'm finding that it's more stable as I alter the control now to alter the frequency. I'll just step it up in frequency again, so it is much more stable if I earth the casing of the potentiometer, so it's obviously getting pickup if we don't earth that. But I may look at using a different type of potentiometer, but a quality one, as we finalise this little project. But for the moment I'm going to leave it there, and in part 2 we'll have a look at ways of trying to overcome some of that instability at the higher frequency end of this little pulse generator that we've built. But the duty cycle does work very well, and we do get a nice indication here on the display as a percentage. So overall reasonably happy, but we need to make some improvements on the higher frequency ranges to stop the jitter and instability. But we'll cover that off in part 2 of the project. Well, I hope you found this little project on the pulse generator useful. What I will do in part 2 of this project, add some additional functionality, and we'll do it by adding another PCB module to this project. So the idea is that we can add on to this as we add new features. Also, we have the ability to upgrade the software as we move along with the project. Now, for the time being, what I will do is I'll put a link down below where you can download the artwork for the PCB, the schematic diagram and the component layout, and I'll also put you a link where you can download the software for the Arduino Nano. If you found this useful and of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.